Today, I'm going to be talking about ways of making null effects informative. It's going to be a bit practical, so if you do want to follow along and you don't already have JASP or JAMOVI downloaded on your laptops, you can do that and you can follow along with some of the example analyses. So why is this even important? I think within most areas of psychology, we are working within this hypothetico-deductive framework of testing hypotheses and, but most importantly, we need to be able to actually falsify hypotheses. In order for us to move our fields forward, we need to be able to falsify our hypotheses. But the main tools that we use within a frequentist framework, we can't actually falsify our hypotheses. We can either reject or not reject the null hypothesis. Yet, we find ourselves in this situation where we're not using the tools that we need to actually apply the philosophy of science that we do when we're actually doing our research, whether we actually realize it or not. So with traditional p-values, you can only reject or not reject the null hypothesis, but you can't make any inferences about the null hypothesis with these traditional methods. So we can't actually falsify our theories. Maybe you want to falsify your theory, or maybe you have a certain research question where you actually want to demonstrate equivalence, or that two groups are actually similar on some sort of measure, or perhaps you're looking at a correlation and you want to demonstrate that there is in fact no correlation. So either you want to test a specific hypothesis for equivalence, or you want to be able to actually rule out that you can actually falsify a particular hypothesis. Quite often, at least historically, a lot of people, this is what I thought when I actually was in undergraduate psychology, is that when you look at a p-value and it's like 0.8 and you're like, well, it's a really large p-value, it's really a lot of evidence for the null hypothesis. But it doesn't actually work that way. A non-significant p-value, regardless of its size, you can't tell whether it is in fact for support for a null hypothesis or whether the data was simply insensitive. An alternative way to actually look at this is using a Bayesian framework or using Bayesian hypothesis testing. So here, there's an application using the Bayes factor. And with the Bayes factor, you can quantify relative evidence for a null hypothesis against an alternative hypothesis. And the benefit of this is expressed in a really easy to understand odds ratio. When we're using traditional p-values, you have to look at a p-value to actually look at the claim of was this hypothesis supported or not. And secondly, you have to have some sort of other measure of effect size to look at the magnitude of support. So it's like a two-step process. But with Bayes factors, this process is combined into one step. There have been ways proposed of interpreting the size of the Bayesian grades of evidence. So if you do an analysis, which we're going to go into, and there's 3 times more evidence for a null hypothesis relative to the alternative hypothesis, you would say, well, this would be moderate evidence for the null hypothesis. And this goes both ways. So evidence can either favor the null hypothesis or it can favor the alternative hypothesis. So these are just suggested frameworks for how to actually interpret this and understand this. But we kind of almost don't need it. We almost don't need these things because it almost seems very intuitive to say there's 10 times more evidence for the null hypothesis compared to the alternative hypothesis. With effect sizes, we know there are effect size thresholds for what constitutes a small, medium, or large effect size. Whether the meaning of that is a lecture for another day. But in that sort of area, it's very hard to know, like, what does an effect size of 0.02 actually really mean, or a Cohen's d of 0.02 really mean? But with this sort of framework, you can actually look at and you can quantify using easy to understand language. There is 3 times more evidence, there is 4 times more evidence, etc., etc. But like p-value cutoffs or like effect size thresholds, these grades of evidence are largely arbitrary. But I think especially now as this sort of idea is catching on, it's good to provide a common point of reference. But because of the interpretability, researchers are less reliant on these cutoffs. And when it comes to how important these cutoffs are, I think it's important to recognize that really extraordinary claims require more extraordinary evidence. So rather than saying, well, we're happy with 3 times more evidence or 5 times more evidence, maybe you want to say 10 times more evidence. And I think if you are taking the approach of if you are pre-registering your analysis or you're doing a registered report, it is also a really good idea to pre-specify of what sort of grade of evidence you think is important. So perhaps you might say, well, if I'm taking a pure Bayesian perspective, that if there's 10 times more evidence for the alternative compared to the null, I'm satisfied that this claim is supported. These things are good to specify ahead of time because doing this post hoc, yeah, there's some issues there. But of course, post hoc analysis is okay in its own right, as long as you're transparent about it. Actually comparing what these mean, so you can take a set of data and analyze it using a traditional p-value inference, or you can use Bayes factors. And roughly speaking, if you have a p-value between 0.05 and 0.01, that roughly corresponds to a Bayes factor of 3. So that gives you an idea of, if I'm looking at and doing some analysis and get a p-value of around 0.05, this will roughly correspond to a Bayes factor of 3. But yeah, so this was an interesting analysis on, I think it was 855 effect sizes there. So you can see how these things roughly correspond with one another. I'm going to demonstrate how to do these sorts of analysis in JASP. Fantastic, free, open source software. It is point and click. There's a number of developers working on this, lots of new features coming. A recent feature which actually I'd only just discovered as I was preparing this is now there is a direct way to actually export R output. So if you want to actually report your analyses, you can actually share the JASP file and people can point and click and go through that, or you can actually report your JASP analysis through an R file as well. Benefit with JASP is it has both Bayes and traditional p-value inference. SPSS now has Bayes as well, so they're also catching up, but it's not open source. You can import SPSS files, so if you have a collaborator or if someone's shared a file and it's SPSS, it's very easy to import, and it's very easy to save your analysis for easy dissemination. Bonus with JASP is if you share a JASP file on Open Science Framework, it actually the analysis actually renders within Open Science Framework, within the browser window. So it's a really easy way to communicate your research. I also think the default figures, they're pretty good for default. Not as good as if you were to sort of tweak it a bit in R, but the defaults are not so bad. So for an example of how we can actually look at null results, I'm going to talk about a paper which was published almost 10 years ago. Unsurprisingly, most of my examples are about oxytocin because that's my field of research and I like actually applying these things on oxytocin. This particular study was looking at the effects of oxytocin administration on spirituality. It's been suggested that oxytocin actually connects you with other humans. In this particular study, they were looking at, well, does it actually connect you to a higher being or just to the world in general? So in this particular study, oxytocin was administered and they were asking questions about spirituality. To the author's credit, the data was posted online and they were asking these questions. Does a single dose of intranasal oxytocin, if we experimentally increase oxytocin levels in the brain, do we actually increase self-reported measures of spirituality? They either got oxytocin or placebo, and they were also measured 1 week later. But we're just going to be looking at the data for when they were first administered the oxytocin or placebo. And they were asked a simple question. Right now, would you say that spirituality is important to you? So between participants, either administered oxytocin or placebo. Again, to their credit, and this was almost 10 years ago, they published their data, which was fantastic, which means it's very easy to go and verify their analysis and also use it as an example to see are any claims of non-significance or claims for a null effect actually supported by the analysis. So for the example data set that I'm going to show you a link to soon, I've removed the variables that we don't need. And in the actual paper, they removed 4 participants. I don't remember why. So I've done exactly the same thing in order to replicate the actual analysis. So I've created this data set on at this link here, which you can look at now or you can look at later. And with JASP, you can open up CSV files and you can load it up and you can see the interface here has, quite a lot of similarities with SPSS. And like SPSS or like other software packages, you have to make sure that continuous variables are labeled as such and they're in the right structure there. And you can easily change these things. So as an example, analysis, before performing this analysis, you might want to ask the question, well, is spirituality related to age? Perhaps people who are older are more spiritual or less spiritual. So for this particular analysis, you can see the window here. I'll bring up JASP as well. Okay, that's not going to work. And you simply drag in your variables there. So we have two variables, age and SP1_1_L is the spirituality measure that we're interested in. And this is just performing traditional statistical inference. Here is your scatter plot. Doesn't look super convincing. Looks pretty flat. The conventional analysis supports this. Pearson's R is very small, pretty wide confidence intervals. And here we have a p-value of 0.75. Traditionally, this would be quite large, but still, you cannot say whether this is actually supporting the null hypothesis or whether this is due to insensitive data. So, for the Bayesian approach, we're going to be comparing two models. The null hypothesis model, that there's no correlation, as in that the correlation is 0, and the alternative hypothesis that there is actually a correlation between these two measures. The input screen looks fairly similar to the frequentist inference. We're dragging the same variables across, but we're doing adding a little bit more extra information in terms of analyzing specific pairs. The reason this is the case is this analysis is set up for large correlation matrices, whereas here we're only interested in one pair. So we drag these pairs together, and we're also ticking a few of these things to get some information here, particularly when it comes to the prior and posterior plots, which I'm going to get into, and Bayes factor robustness checks, which I'm going to get into as well. So far, this is similar to how you would do a frequentist analysis. And this is the plot that we get that I'm going to walk through. When it comes to Bayesian analysis, we set a prior belief of how we think the data should behave. So here, with this dotted line here, we're saying, with this prior belief that we've set, that any correlation between -1 all the way to 1 is equally plausible. Now, this isn't the case. I can't really think of any sort of thing other than something that's completely random where any of these correlations are equally plausible. But to begin with, this is the assumption that we're taking. So we have no reason to suspect that any value of p is more likely than any other value. So this dashed line, this represents our prior belief of what this relationship actually is, and that here, that at this relationship, we actually have no idea whatsoever, and we think it could be anywhere across from -1 all the way to 1. So now, with our Bayesian hypothesis testing, we're testing how the observed data updates this belief with the posterior distribution. And so here, assuming that the correlation is 0, the posterior distribution, which is actually our observed data, is almost 6 times higher than the prior distribution. So here, we can say, assuming that this is our prior belief, that there is 6 times more evidence for a null effect compared to an alternative effect. This is the sort of thing that we couldn't get with the p-value that we originally indicated here. And we're looking at this value here, BF01, which is the null hypothesis relative to alternative, and here JASP also reports the evidence for the alternative compared to the null, which I'm going to get into a little bit more here as well. Yeah, these values are simply the inverse of one another. So you have to think about, what am I interested in? Am I interested in reporting the null relative to the alternative, or the alternative relative to the null? 1 being the alternative and 0 representing the null here. So here we're interested in the null, and we can see that the relative evidence is 6.738. I want to talk a bit more about these so-called pizza wheels. So this is a way of actually visualizing the relative evidence between the alternative and a null, with the red area representing the support for the alternative hypothesis and the white area representing the null. So the top panel represents what we would roughly correspond to 0.05, which really makes you think when you're looking at a lot of the papers within our field, which are hovering around 0.05, this is the actual relative evidence between the alternative and the null. So this is a really good visual indication of the relative evidence between these two hypotheses that we have. You can select what you want reported in your output. Within the plots, both the Bayes factors options, alternative relative to null and null relative to alternative, are reported, but when it comes to the actual output that's reported, you can choose that there. Like I said before, we were previously going by the assumption that there is equal probability for all these correlations. when that really isn't the case. So what you can do is you can actually adjust your prior distribution or your prior belief. Here we can see that there is much more, whether we believe there is much more chance that the correlation is 0, or there's much less chance that the correlation is either 1 or -1. This is perhaps, this is a more realistic, for most fields of psychology, correlation effect size here. We've adjusted this, and here with this adjustment we can actually see this slightly adjusts what our base factor is here. So here we can see with this more realistic prior distribution that there is 4.5 times more evidence for the null compared to the alternative. So slightly less, but it doesn't change it too much. So not only does this result provide relative evidence for one hypothesis over another, it also conveys the magnitude of this, 4 to 6 times depending on the prior distribution that you use. Now you're probably thinking, well, this is kind of like p-hacking, where you can sort of adjust a few things and get what you want, or it's been called b-hacking, where you can sort of, what if we just kind of tweak our prior, maybe we can get the result that we want. That's why it's really important to do this base factors and robustness check. Well, firstly, if you can do it, you should actually be pre-registering what your prior distribution is. If you're submitting a registered report to most journals, they will ask you what ways you're actually going to be evaluating evidence for the null hypothesis. And if you're taking a Bayesian approach, they will ask you to pre-specify your prior distribution, and reviewers will read that going, well, that is plausible, or that is not plausible, so you can pre-specify that. But in cases that you can't pre-specify that, you can do these sensitivity analyses or these robustness checks where you can actually see for a range of priors, for a range of stretch priors, so basically going from flat to more curved, how does the evidence change? So here we can see it's not super sensitive to the prior that you choose. So if you're doing this, if you haven't pre-specified your prior distribution, make sure you're posting and sharing these robustness checks just to demonstrate that your result or your conclusions are not sensitive to the choice of prior. One more example I use is looking at t-tests, which is another common test. So here we're looking at the primary outcome, whether intranasal oxytocin increases feelings of spirituality. We can do our conventional test. You can see even within JASP we can do very nice rain cloud plots here, which is part of the t-test analysis suite. And you can drag across your variables into the grouping variable. In this case it's oxytocin or OT condition, and the dependent variable here, which is the report of how spiritual do you feel right now. Traditional Welch's t-test revealed no difference. So looking down, we have a p-value of 0.259. But again, we can't make any strong conclusions based on this p-value alone. It's either due to support of a null hypothesis or the data was insensitive. So we have to investigate, was it underpowered, or is it truly, or is it consistent with a null effect? Again, we drag our variables across much like in the same way. And yeah, it looks very similar to how we're doing our correlation. And at the bottom here, we can specify our prior distribution. A default Cauchy distribution with a scale of 0.71 is there. This has been recommended or included as the default because it sort of corresponds to the sort of findings that we see within psychology. But again, you can adjust this. You can look at the prior distribution and think, is this actually realistic? Okay, here we go. So you can see the example here about a prior distribution. It has a lot of weight around an effect size of 0. That's pretty plausible. Effect sizes beyond 1 are less plausible. There aren't that many. Maybe perceptual psychology, you can begin to see some pretty hefty effect sizes, but within many areas of psychology, an effect size of Cohen's d beyond 1, yeah, that's less likely. But that's up to you, and that's up to you to think about your own research field, to think about what sort of effect sizes are realistic. So in this particular case, there was only 2.4 times more evidence for the null hypothesis compared to the alternative. Remember, BF 0, 1. BF 0, null hypothesis, compared to 1, the alternative hypothesis. 2.4 isn't great evidence. So this suggests that this test was underpowered and we cannot make any strong conclusion either way. So yeah, 2.4 times more likely that the null is more likely than the alternative hypothesis. Thinking about the prior distribution, perhaps you have pre-specified an hypothesis that group 1 is bigger than group 2. So you don't think there's actually going to be anything on this side of this effect size because the effect size is going to be positive. You can adjust your prior distribution to reflect your hypothesis. But here, it didn't make too much difference. There's still slightly more evidence for the null, 1.4. So it's even more inconclusive here. There are other ways that you can adjust your prior distribution. In many fields, you may not actually expect for this to center around 0. Maybe within your research field, you have a good understanding that, well, effect sizes tend to hover around 0.2. You can adjust your prior in that sort of way. So here, we've adjusted our prior to roughly, at the time at least, the average effect size in oxytocin research, which is 0.28, which hasn't actually been adjusted for publication bias. And we can also, for argument's sake, specify a tighter distribution. So this distribution here with the dotted lines basically says that, you know what, I think that effect sizes larger than 1 are basically not possible. You can adjust that depending on your understanding of what the literature is and your understanding of the research field. So again, only slightly more evidence for the alternative hypothesis in this particular case there too. So this is an example of, depending on, this result doesn't seem to be very sensitive to the choice of the prior distribution. So looking at this, if we were doing this analysis in a traditional paper and we were just looking at the correlation, for the correlation we would say there's a non-significant relationship and that's all that we can say. We couldn't say that there is no relationship between these two factors. We could only say that this relationship was non-significant. It's an important distinction there. But if we're doing Bayesian hypothesis testing, we can say there's almost 7 times more evidence for the null hypothesis compared to the alternative. When it comes to the t-tests, both approaches are inconclusive. So we have a p-value of 0.26, which is non-significant, and we only have 2 times more evidence for the null hypothesis compared to the alternative. So a little bit quite inconclusive there. So in summary, for Bayes factors, we have an easy to interpret measure of either support for the null or the alternative hypothesis, which is relatively straightforward to do within JASP. I personally recommend that you should present these alongside p-values. It's a risky play that I think just presenting this, because reviewers are going to go, where are the p-values? They're expecting the p-values, but there's nothing wrong with presenting these side by side, or almost doing this as sort of a, well, we did an analysis, there was a non-significant p-value, so to better understand our data, we went on to do Bayes factors. Maybe in a couple of years' time, you can present data that's just Bayes factors alone, but I don't think we are quite there yet for most fields. Maybe in your subfield it's different. I've presented very straightforward analyses of correlations and t-tests. I have written a longer tutorial paper which includes ANOVAs and ANCOVAs and chi-square tests. But of course, real life data is more complicated than that. And Bayes factors are really good for linear models or any sort of model that you're fitting. If you want more flexibility, I would suggest the Bayes factor R package to compare your models within a Bayesian framework. Okay, that is Bayes factor analysis, but what if you want to stick with a frequentist framework and not go with Bayes? You can do that. Within frequentist hypothesis testing, you can't support an hypothesis that an effect is exactly 0, but you can reject effects that are large enough to be considered worthwhile. So you can provide enough evidence for the absence of an effect that's large enough to be considered worthwhile, which is also known as equivalence. Now, equivalence testing has been around since the 70s. It's been quite popular within sort of pharmaceutical sciences. It's only really taken off within psychology, maybe within the past 5 years, probably because it wasn't actually included as an option within SPSS until relatively recently. Yeah, it's because it's unlike with Bayes factors, which are Bayes factor analysis, which is computationally expensive, or it can be at least. This is relatively straightforward in comparison. With sort of like with Bayes factors where you have to specify prior distribution, with equivalence testing you also have to specify upper and lower equivalence bounds, or the sorts of effect sizes that you consider to be equivalent. So let me walk you through this figure. We have 4 different possible scenarios. So here we have some sort of test that's looking at mean differences here, a range of effect sizes, let's call them Cohen's D, and in this particular scenario we're saying that effect sizes between minus 0.5 and 0.5 can be considered to be statistically equivalent. Yeah, not many fields that might be relevant to, but for the purposes of the demonstration, let's go with that. Like traditional statistical inference, any time that the 95% confidence interval crosses 0, we can say that this is not significant. But in this case, we have the thin lines and the thick lines, where the thin lines represent a 95% confidence interval and the thick line represents a 90% confidence interval, which we use for equivalence testing. So if a thin line, i.e. the 95% crosses 0, then we have a non-significant result. However, if the thick lines fall completely in between the bounds that we've specified, we can also say that these results are statistically equivalent. So on the top, we have a scenario where it's crossing 0, but it's also fully within the bounds. So this test would be statistically equivalent and not different. Second scenario, we have something which is not crossing 0, and is also not crossing the equivalence lines as well. So this is different and not equivalent. The third scenario is equivalent and also different. I often get asked, look, in what sort of scenario do you often get this? And I remember there was an experiment done by Facebook a couple of years ago where they said, what happens if we manipulate the sort of things that we see in your feed? Is that actually going to influence how people actually post later on? And so I'm not sure about the ethics of this, but they basically manipulated and let some people see more positive stuff and some people more negative stuff. And they actually noticed, and there was a press release going, yes, Facebook is good for the world. If we show people more positive things, they're going to post more positive things. P-value was tiny. And then someone asked the question, well, what was the effect size? But the effect size was like 0.001 because their sample size was enormous. So that's an example here that although it was a significant result, you have to think about, is it actually meaningful? And because the effect size was so tiny, or the actual equivalence bounds were so tiny, you would say in that case, yeah, it was significant, but it was kind of equivalent as well because the results were so tiny. Then we have the fourth scenario where something is not equivalent and not different. This is quite common when you have very underpowered research, where the bounds, when you have a small sample size, are quite wide, where you can't make any conclusions. Unless, of course, you wanted to increase the equivalence bounds, and you can do that, but you need to think about, well, if the equivalence bounds were around 0.8, does that even mean equivalence? In most fields, typically not. So that is the 4 possible results that you can get when you're doing equivalence testing. How do you set your bounds? This is not necessarily easy. You can think about, well, what is a just noticeable effect? In some areas, for instance, perceptual psychology, the ability for a human to perceive a particular light source, for instance, you can actually specify that. But in many areas, you can't really specify what a just noticeable effect could be. If you really want to, you can use Cohen's effect size thresholds. Probably not the best approach, but it is a approach as well. But the most important thing is that you justify it. You may actually say, you know what, I have no idea what my equivalence bounds should be, so I've just gone with small. At least you're transparent with what you actually did for that. You can be even more straightforward and think about your resources. You can do power analyses for equivalence tests. They're very similar to a power analysis for a conventional test. Typically, you need about 5% more participants for an equivalence test than to do the equivalent thing for a traditional test. But think about, what do you actually have sufficient power to detect based on the resources that you have? That is one approach. Regardless of how you do it, pre-specify and justify your choice. But if you haven't pre-specified it, then kind of like the Bayesian robustness checks, demonstrate your results for a range of equivalence bounds. But the good thing is it's extremely transparent. If you're making claims, so going back to this thing, if you're stretching your equivalence bounds to 0.8 and making claims, our effects are equivalent, readers can look at that going, is 0.8 really an equivalent bound? At least you're being transparent, or you have to be transparent about the claims that you're making. Equivalence tests, I think, are a little bit easier to do within JAMOVI. They are possible within JASP, but I just think the output is actually a bit better with JAMOVI. Very similar to JASP. They actually use the same core engine, so you'll notice a lot of similarities between JAMOVI and JASP. But again, we're doing a demonstration here looking at an equivalence test for t-tests. Choosing your variable, here again we're going back to the spirituality measure and also the grouping variable of oxytocin condition. And here we've set our equivalence bounds between minus 0.2 and 0.2. So here we've gone, well, I don't have a really good understanding. I'm going to fall back on Cohen's recommendations for what constitutes a small effect size. And our results here, so they're not different and not equivalent. So here it spells it out for you. You can't reject the null significance hypothesis test. And for TOST, which is the two one-sided test or the equivalence test, you can't reject the equivalent hypothesis. So we can visualize that. So here's the effect down here. We can see our bounds that have been set. Yeah. This is what happens when you actually adjust the equivalence bounds. So say I was being very ambitious and thinking, well, what happens if I actually set the equivalence bounds to minus 0.8 to 0.8? Here you can see they fall well between those two bounds there, and we can see that the traditional null hypothesis significance test, we can't reject it, but we actually can reject the null equivalence hypothesis. So this supports that these results are equivalent, assuming that these equivalence bounds are actually realistic for your research field. So again, you need to really think carefully about what equivalence bounds would be for your field. If possible, pre-specify them before your analysis, and if you can't pre-specify them, actually demonstrate what these results are for a range of results. Same sort of deal when we're looking at correlations here. We simply put the variables in there, set our equivalence bounds, except here we're using R rather than Cohen's D. So for this particular example, if we're using these equivalence bounds of minus 0.3 and 0.3, these results are actually equivalent. We can see the results here. The TOST result, true, significance test, false, and visually we can see that there is it is well within the bounds there as well. So yeah, very nice visualizations within JASP. I want to give you, or at least I want to finish off with a discussion of some real-world applications of this. So of course, you can use these sort of approaches within your own research. Within your own research, you can think about, do I want to actually demonstrate evidence for a null effect? Or you can actually look back at prior published research to go, has published prior research which has made claims about null effects actually a null effect? I did this a couple of years ago. A lot of people came out to say, well, you know, there's a lot of positive effects for intranasal oxytocin, but there's a lot of negative effects. Because of these negative effects, we should abandon the field. The field is dead. Look at these large p-values. So I went back and evaluated a bunch of studies. This was 107 studies, which were synthesized across 35 meta-analyses. And I set a range of equivalence bounds. I didn't really pre-specify this, so I actually demonstrated, can't see it very clearly here on the slide, but there's, I think it's 0.1, 0.2, and 0.3, I believe. And you can see what happens when we actually reanalyze all these results. So, considering that at least the publication bias adjusted effect size for oxytocin's effects are around 0.5, I did these equivalence bounds, and no meta-analyses were actually equivalent. So assuming equivalence bounds of 0.1, no meta-analyses were equivalent. But once you actually stretch out the equivalence bounds to 0.2, which is kind of in between this sort of realistic effect size, then some of these meta-analyses were equivalent. So this is a potential thing that you can do within your own field. Think about maybe there's a meta-analysis which is making claims about this. Maybe there's a bunch of studies which are actually saying, well, there are no effects. We need to abandon this theory. You can reevaluate this using either Bayesian hypothesis testing or equivalence testing as well. So this basically, the main result here is we don't have enough data. The sample sizes are too small. If the sample sizes were larger, we'd actually have a better understanding. We did a reanalysis of this recently, and we still have the same problem. We have a little bit more precision, but still not enough precision to make any strong claims here. So that is a very quick introduction to equivalence testing and Bayesian hypothesis testing. Hopefully this has inspired some ideas for your own research. You can go back with the research that you've done or other published research and reanalyze stuff, or you can include this within your own toolkit as well.